defects of the eye. So, what are the optical defects of the eye that will make our visual system is not seeing everything clearly? Like as I said in the first lecture of the optics, the eagle, for example, can see the fish in the sea from a large distance, and other animals can see at a longer distance than the human being. So why don't we see that from a large distance, or why don't we have this super ultra normal vision? This is because there are some optical defects of the eye that we mentioned one of them in the first lecture, which is the diffraction. These optical defects of the eye can be either physiological or pathological. The pathological that occur at some patients, which are the errors of refraction, and these errors of refraction like myopia or hypermetropia or astigmatism have been already discussed in the previous lectures. So today we are going to discuss the physiological optical defects of the eye. One of them has been already discussed, which is diffraction. So today we are going to cover the chromatic aberration, the spherical aberrations, and the peripheral aberrations. So aberrations meaning that it is like a deviation from the normal or deviation of the light from its normal pathway. This can be either chromatic or associated with color defects, spherical or due to spherical error or due to defect in the spherical surface, or it can be due to peripheral, or it occurs only to the peripheral rays, not to the central rays. So let's cover the physiological defects, starting first with the chromatic aberration. Chromatic aberration meaning that the image looks blurred with different colors like this. So why does this chromatic aberration occur? Let's revise some basic rules that we mentioned in the early lectures of optics. So we said that if we have a white light that enter into an interface or optical interface, this white light will undergo dispersion. This dispersion is due to the components of the wave, due to different colors according to the wavelength. Also, it will deviate to the spectrum of visible light, starting or ranging from the red color until they reach the blue color. So this deviation occurs due to the different wavelength and the different frequency of each one of these lights. So chromatic aberration meaning that it's a property of a substance to produce refraction of light of shorter wavelength more than the light of longer wavelength, meaning that the blue light is refracted more than the red. So again, in this example, you can see that the white light here is entering into a refractive medium, and this refractive medium will cause dispersion of the light, and this dispersion is more for the blue, so the blue is bent more while the red is bent less. This property is called chromatic aberration. So we have a white light. This white light now is producing images of different colors. So as you can see here, this is the white light entering into this lens, and by entry into this lens, the lens will cause dispersion of this light. This dispersion occur more at the periphery because we mentioned before that the periphery of the lens has a prismatic effect, and this prismatic effect will cause dispersion of the light, leading to dispersion of the blue light more than the red, as you can see here. So this will lead to the formation of different foci of the light. So it will be, there is a blue focus, there will be green focus, there will be yellow focus, there will be a red focus. This is what is meant by the chromatic aberration. So in a perfect optical system, the light will enter inside the lens, and then it will make a focus, and this focus will be a single focus of a single color. However, what happens is that when the light enters in the periphery of the lens, it will lead to dispersion, leading to the formation of the different foci. So each color will make a focus of its own. The blue light will be more close to the lens, and while the red will be more far from the lens because the blue is deviated more while the red is deviated less. Again, the shorter the wavelength of the light or the blue colors are bent more, while the longer wavelengths like the red are bent less. So the blue is deviated more than the red. So as you can see here, if the white light enter in the lens, this will lead to dispersion of its colors, leading to formation of a focus of the blue light, which will be closer to the lens, and then the white light or the yellow light will be in the center, while the red light will be the most far from the lens because it is the least deviated. How can we apply this to the eye? If a white light enter inside the eye like this, then the yellow light will be focused on the retina, while the red eye will be focused outside the retina, so it will be behind the retina, and the most short wavelength, which is the violet light rays, will be focused in front of the retina. Again, the red light will be focused behind the retina, the violet will be focused in front of the retina, and the yellow will be focused on the retina itself. So, does chromatic aberrations occur at the human eye? The answer is yes. So, refraction by the human eye is subjected by chromatic aberration. There will be a total dispersion from the blue to the red image in about 2 diopters. So, if we have here this range from the blue to the red color is about this range is equal about 2 diopters. And the emmetropic eye will focus the yellow-green light at about 555 nanometers. So the yellow light that has a wavelength of 555 nanometer, this is the light that will be focused immediately on the retina, while the blue light will be focused in front of it, and the red light will be focused behind it. So why doesn't we see the blue each image with blue and red halos of light due to the chromatic aberration? This is because we have some certain mechanisms that neutralize the chromatic aberrations at our eyes. First of all, we have small pupil size. So this small pupil size will limit the amount of peripheral light rays that will enter inside the eye that will undergo the prismatic effect that will lead to chromatic aberrations. So small pupil size will allow only the axial or paraaxial rays to enter inside the eye, making that this light having undergo or will have minimal spherical aberration due to minimal dispersion. Also, the eyes has a tendency to make a sharp image of the yellow and neglect the red and the blue portions. So if our eyes see a target or see an image that has been manipulated by chromatic aberration, our eyes have the tendency to see the yellow more clearly than the red and the blue, so that they will neglect the yellow and the blue. Also, we have what's called chromatic magnification. So chromatic magnification meaning that our eyes can see that the different images of the same object of different colors by different sizes, so that the yellow size or the yellow image will be the most larger one or the most appropriate size, while the red image will be larger and the blue image will be the smaller, while the yellow image will be of the appropriate size. This is because the fovea is eccentric, it will show that error. Let's see this example. This is what's called the chromatic difference of magnification. So if we see a target, and this target has emit light rays that enter inside the eye, and this will form a blue and yellow and red image. So as you can see, since the blue is closer to more toward the lens and the cornea, so the blue image will be smaller, and since the red image will be more far, so the far image will be larger, and the yellow image will be of the exact size of the image of the object. So our eyes are has a tendency to see the image of appropriate size. So if they see a small image, they discard it or they neglect it, or if they see a large image, they will neglect it. So not only they neglect the colors, but they neglect the abnormal sizes. Then this is called the chromatic difference of magnification. The applications of Okay, Dr. Magid, when I see an area that is common in the MCQ, I will mention it. So, okay, so the application of the cobalt blue glasses, so it will be, or the applications of the chromatic aberrations, it will be the cobalt blue glasses. First, what are the cobalt blue glasses? The cobalt blue glasses are a type of glasses that will allow only the red and the blue light to enter inside the eye. And by the difference in the chromatic aberration, we'll be able to know if the eye is myope or hypermetrope, meaning that if the eye can see the red color clearly and the blue is blurred, then the eye is myope. If the blue is seen clearly and the red is blurred, then the eye is hypermetrope. Let's see this example. Here we have if the patient wear the cobalt glasses, then this cobalt glasses will allow only the red light and the blue light. So if the patient see the red light more clear in the center, surrounded by a halo of the blue light, then this meaning that the eye is large, and this also, if the eye, on the other side, if the eye can see the blue light more clearly, so the blue light will make a central circle and surrounded by a haze or surrounded by area of haze of red color. This means that the eye is short since can be seen the blue light clearly. So this means that this eye is hypermetrope. The second most widely used application of the chromatic aberration is the duochrome test. And by its name, duochrome test is the test that has two colors. So du meaning two, chrome meaning color. So this is the test that has two colors. This test is very important in practice and also very important in the MCQ. It is frequently asked. So what is the duochrome test? It is a test that is used to know if the patient is more myope or more hypermetrope by presenting the two different ranks of colors, the red and the green, and asking them or asking the patient to compare between the letters or the optotypes in between these two ranks. So these two ranks can be either horizontal like this, or so it could consist of two ranks of black Snellen letters against illuminated color glass. It could be the upper and lower or right and left. So can be different shapes or different patterns of the duochrome test. The optical principle of the duochrome test is the same like chromatic aberration. So when we are placing lenses in front of the eyes, this lens has a prismatic effect of its periphery. So the lens substance will cause a dispersion of the color into constituent colors, starting from the red to the blue. So the red color will be deviated less and will make a focus behind the eye, while the blue color will be deviated more, making a focus inside the eye or in front of the retina, with other colors making different foci in between. So this test is used for detection of the refractive error of the patient, meaning that if the patient is myope, then this patient will see better, as their eyes are large, or if they are hypermetrope, they will see the green better. while the emmetrope will see the yellow color clearly. So why do we use the red color and the green color instead of the red and the blue? This is a very common question. Although that the blue will tend to deviate more than the green, the green, as they straddle the yellow light by equal amounts, meaning that they are separated from the yellow color, which is focused on the retina, by a small different or a small similar amounts of zero point 0.4 diopters, so that when we compare between the brightness of the red and the green color, then the patient will his response will not be biased by the relative distance of the different colors from the retina. So how can this test be done, or how can this test be performed? The patient is viewed the letters and he is asked which set appears earlier. So if you report that the red appears earlier, this means that the patient is more myope. If the patient says that the green is more better or more clear, then the patient is more hypermetrope. And this test is very sensitive, even up to 0.25 diopters. So we can even increase and decrease refraction by increments of 0.25 diopters if the patient is saying that the image or the object or the Snellen chart appear more bright or less bright on any one of the colors. So the result is that the myopic patient will have longer eyes and the powerful eyes, so they will see the red better. And the hypermetrope will see the green better because they have smaller eyes or they have a weaker optical system. So the main importance of this test is in case of refraction of myopic patients, because myopic patients can be easily overcorrected, because if we overcorrect the myopia, and the patient will still be able to compensate for this overcorrection by their accommodation. So for example, let's say that if a patient has a refractive error of -3, and while we are doing refraction for him, we put him a glass of 3.25 diopters. The patient with this refraction can still see 6.6. This is because the patient is able to overcome this extra 0.25 diopters by his accommodation. So he can accommodate, leading to overcome of this refraction. So what will be the problem if the patient accommodate? The problem is that the patient will complain from headache and severe spasm and athenopia because of constant strain on his eyes. So we need to relieve this by making sure that the patient has its own accurate refraction and not overcorrecting his minus. How can we do so? Can be done by the duochrome test. So when we are presenting the red and the green ranks, the patient is asked which one of them is better. If he can see that the red better, then this means that the patient is more myope, or he can see more clearly because he has more powerful optical system, so that he doesn't need to any further modification of his refraction. And also, if the patient can see equally both of the red and the green equally clear, this means that the patient has a powerful optical system that can see clearly without the use of accommodation. The problem comes when the patient says that he can see the red color better. If the patient see the green if the patient see the green color better, if the patient see the green color better, meaning that the patient has either a small eye or he has over accommodate, he is having a weak optical system, so that the green color is focused on the retina. And this means that the patient, in order to see clearly, he will have to use his accommodation. And this what will make him complain. So, and if the patient see the green color better, then we need to increase his refraction by plus 0.25 diopters increments until he sees that the red and the green are equally clear, or the red is much more better. I hope that this is clear for you. One of the very important topics or questions in the MCQ is asking about color blind. If you have a patient who has color blindness, does this invalidate the test? So you cannot use the duochrome test on a color blind patient? What do you think? Yes, as the Koshadi says, it could be. Why? Because we don't test the appreciation of the color of patient. We don't ask the patient to name the color. We don't ask the patient to see the red as red and the green as green. But we ask about the relative appreciation between both colors. So you can ask the patient to report if the upper rank is more bright than the lower rank, or the right rank more bright than the left rank, even without saying any color at all, because we don't test color discrimination. We test the color brightness and appreciation relative to each other. So whether the patient says see the red as red or green as green, or whatever the color that he can see, he will be able to appreciate the difference in brightness between both of them if he has a refractive error. The third application of the chromatic aberration will be the achromatic lenses. What are the achromatic lenses? From its name, means absent, chromatic, so there will be no chromatic aberrations of these lenses. These are composite lenses. They are lenses made of different materials combined in such a way that will neutralize the dispersion. So they are combined so that the dispersion is neutralized while the overall refractive power is preserved. So let's say, for example, that we need to make a glasses or make a lens which is +3. So in order to make a lens +3, we can use a biconvex lens of +3. But in such a condition, this lens will have a large dispersive power and it will cause much chromatic aberrations. Instead, we can use what is called achromatic lens. So we can combine a convex lens of high refractive power and low dispersive power, and a concave lens of low refractive power and high dispersive power. So for this example, instead of using a spherical lens of +6, we can +3, we can use a lens of +6 combined with a minus lens of -3. Again, in order to have a net refraction of +3, we use a lens of high refractive power and low refractive and low dispersive power, like crown glass, which has a refractive index of 1.5, and we use another lens of less refractive power and the high dispersive power, like the flint glass or the compressed glass, which has a refractive index of 1.7. That's how the refractive power of both lenses will compensate for each other, leading to a net result of +3, and the high dispersive power of one lens will neutralize the low dispersive power of the other lens, so that they will neutralize the chromatic aberration of each other. So by making this achromatic lenses, we'll be able to eliminate the chromatic aberrations. Is it clear? So this is the base of the most lenses used in photography, or even the lenses used in ophthalmology. So the 90 diopter lenses and the 80s, the 78, and the different lenses used in ophthalmology are based on this principle. So they combine a crown glass and the flint glass So these both of them will have the crown glass will have low dispersive index, and the flint glass will have high dispersive index. So they will eliminate each other. This is what's called achromatic doublet. And by this doublet, the aberrations are neutralized while we are preserving most of the power of the convex lens, as in case of Nikon lens. The second of all is the spherical aberrations. The spherical aberrations is another type of aberration that occurs due to the prismatic effect of the periphery of the lens. So we said that the axial light rays while entering through the lens will not suffer from any deviation. And as we go toward the periphery, the lens will have a prismatic effect that will cause deviation of the light rays. So the deviation is least at the paraaxial rays, and as we go toward the periphery, the deviation will be more occurring. As you can see here, that as we go toward the periphery, the lens will be more deviating the light rays due to the prismatic effect. So the periphery of the lens has a higher power due to the prismatic effect, and thus the rays passed through the periphery of the lens will deviate more than the light passing through the center of the lens, and this will lead to different foci. So as you can see here, this is the axial and the paraaxial rays. They will make a focus, and the periphery of the lens will make another focus, and so there will be different foci different from the center and the periphery, leading to, as you can see here, that the light rays will not come to a single focus. As you can see here, this will be the perfect optical system, making the focus a single focus, but this is due a physiological defect or some of the optical defect of the lenses. That is the spherical aberration due to the prismatic effect of the periphery of the lens, causing different foci, as you can see here. So if this is the case in the eye, we will not be able to see clearly. But we have, again, some mechanisms that will neutralize the spherical aberration. The first of all is that the cornea is flat in the periphery. So here is the cornea. So the periphery, which should have the largest power and the largest prismatic effect, is more flat. And by this flattening, this will lead to decrease the spherical aberrations. Also, we have an iris, and this iris will cut the peripheral rays. So if you have a peripheral rays like this, then it will hit the iris and prevent that this peripheral rays from reaching the retina. The central portion of the lens has a greater density. So here is the lens. It has a nucleus. This nucleus has much more refractive index and much more density. Also, the Stiles-Crawford effect. The Stiles-Crawford effect, meaning that the cones are more sensitive to the light rays that will enter the eye paraaxially than the light rays that will enter the eye obliquely through the periphery of the cornea. Meaning that if we have here like a cornea, like a lens, the eye is more sensitive, or the photoreceptors, or specifically the cones, are more sensitive to the light that will hit the retina from the center or from the axial area. However, if there is a light ray that will enter the eye obliquely and they hit the photoreceptors from the periphery, then this light rays and this image will be neglected by the eye, and this is called the Stiles-Crawford effect. So how can we decrease the spherical aberrations? First of all, we make aspheric lenses. So we know there is what's called achromatic lens, and now we say there is aspheric lenses. Aspheric lenses, these are the lenses that has flat periphery. So the flat periphery will eliminate the prismatic effect of the lens periphery, leading to that the peripheral and central rays will come to a single focus. Another form or another type or another method for decreasing the spherical aberration is the form of the lens. The best form of the lens is the meniscus lens, because if we have like a biconvex or a plano-convex lens, this will lead to a spherical aberrations. So as you can see here and here, you can see that the light rays doesn't come to a single focus. However, if we use the meniscus form of the lens, so the plus the it will be combination of plus and the minus lenses, then they will both neutralize each other and will cause combination of the light rays into a single focus. Another method also to decrease the spherical aberration is the lenticular lens. So we put a lens that has a central bulge so that the power or the refractive power of the center become more, and this will lead to that the peripheral light rays will come to in the same focus as the central light rays. So we said the spherical aberration occurs due to increased refraction by the periphery of the lens due to increased prismatic effect. But in case of lenticular lens, we increase also the power of the center, leading to both all light rays will come to a single focus. Another reason or another method for decreasing the spherical aberrations will be to change the orientation of the lens. Meaning that if we use the plano-convex lens, so that if the light rays will enter from the plane surface, then the light is more prone to develop the spherical aberrations by focusing into different foci. But if we make the spherical surface more toward outside, so that this will be more likely to develop a single focus. Again, in order to eliminate the spherical aberrations, we make the focus or we make the light rays hit the curved surface of the lens. Finally, the peripheral aberrations, which are the type of aberration that occur due to the light rays enter the optical system peripherally. So images that will fall on the retinal periphery are not well defined as the central image due to, first of all, the image distortion that will occur due to the prismatic effect of the lens periphery due to unequal magnification. This has been mentioned in the Afikia lecture. So we said that the center will cause a different magnification than the periphery of the lens. This is again due to the prismatic effect of the lens periphery. So if we have this object, if we have a large or high plus lens, this will lead to pincushion effect. Dr. Magid is asking, can we use the meniscus form of the lens or mostly, or they are contraindication? So the meniscus form is what's called the best form lens. So if when we are prescribing glasses to a patient and the optician will make these glasses, the optician makes sure that this glass is always of the meniscus form, because this form proved to have the least aberration. So it will prove to be having the best quality of vision. Again, to the image distortion. So the image distortion occur in case of light rays entering through the periphery, and this light rays entering through the periphery of the lens will undergo the prismatic effect. This prismatic effect will cause unequal magnification. So this unequal magnification will manifest itself as pincushion distortion in high plus lens or barrel distortion in the high minus lens. So as you can see here, this is the barrel distortion, and this is the pincushion distortion, and this is a normal image. Again, this is a barrel distortion caused by a minus lens, and this is a pincushion distortion caused by the plus lens. Other type of the peripheral aberration is called the oblique astigmatism. What is meant by the oblique astigmatism? Oblique astigmatism is a kind of aberration that occurs if the light rays will enter through the periphery of the lens obliquely. Again, here is the central light rays entering through the center of the lens, center of the spherical lens. But what happens if a peripheral light rays enter through the lens obliquely? This will lead to that they will go through the unequal part or unequal refractive part of the spherical lens. This will lead to that this peripheral part of the lens, of the spherical lens, will act as a cylindrical lens. And this cylindrical or spherocylindrical lens will act as a toric lens that will make a conoid of Sturm. So the conoid of Sturm will make two focal lines, as you can see here, and circle of least confusion, as you can see here. So again, what will be the problem? The problem that the peripheral light rays that will undergo this kind of aberrations will fall on the retina and will make confusion, because the image will fall on a focal line rather than to fall as a point in case of a spherical lens. Again, here is the optical axis, and here is the light rays entering into the lens peripherally. So as they enter the lens periphery, they enter into the vertical meridian, the horizontal meridian, and the vertical meridian. So each one of them will form a horizontal line and the focal line, and there will be a circle of least confusion. So these are the results of the peripheral aberrations, or results of astigmatic aberrations. So as we mentioned, that the oblique astigmatism as well as other kinds of aberrations are more common with the biconvex and the biconcave. So these are used as a kind of lenses for vision, or for photography, or for ophthalmology, or any kind of lens that needs a high quality. But rather than we use the meniscus type of lenses. So how can we avoid this peripheral aberrations? The incident light should fall on the center of the lens, so it could be parallel to the axis. So or the patient should be instructed not to look from the lens periphery. Also, restricting the aperture of the lens. So, for example, if it's a lens used for photography, we decrease the aperture of the lens, and we use the meniscus lens. The third type of the peripheral aberrations that occurs due to the peripheral refraction by the peripheral part of the lens is called the coma aberrations. And the coma aberrations, it is a subtype of a spherical aberration that occurs when the oblique light enters through the lens periphery. So apart from the oblique astigmatism that we mentioned, another type of refraction will cause what is mentioned, or what's called the coma aberration. So the peripheral light rays will undergo more refraction than the oblique light passing through the center. So as you can see here, this is the oblique light passing through the center. It doesn't go much refraction, so it will make like a focus here. However, the oblique light passing through the periphery of the lens will undergo more refraction and more bend, leading to formation of a different focus. So the focus, instead of being a single point, the single point will have a shadow like a coma, and that's why it's called a coma aberration. So again, here is the refraction by the central light rays, like here, and these are the refraction by the peripheral light rays, making an extension of the central one, leading to the shape of coma. So here, if we have no aberrations, as you can see here, but here if we have a coma aberration, you can see the central light, but with a halo of light extending from one edge to appear like a coma. And here's the difference between the spherical aberration and the coma. So if a patient has a spherical aberrations, he will see that there will be glare concentric with the object at all directions. But in case of coma, it will be extending only in one direction. So coma aberration basically results in unequal magnification of the image by the different parts of the lens, leading to oval or coma-shaped magnification. So again, the lens periphery is the one in charge. The lens periphery was causing different magnification size of the image, leading to that the original image has a shadow of different size, leading to the coma shape. So how could it be neutralized? The aberrations or these aberrations or these coma aberrations can be neutralized by the human eyes or occur in the human eyes by the effect is minimal because of the more or less the same reasons of the elimination of the spherical aberrations. So the cornea is aspheric or flattened in the periphery, so that the periphery of the cornea doesn't have much greater refractive power, and thus it will eliminate the effect of unequal magnification and will decrease the coma and spherical aberration. Also, the retina itself is not a plane surface, it is a spherical surface, so the circle of least confusion formed by the conoid of Sturm is falling on the retina. So here it will be the unequal magnification here, it will be the same like or the same effect of the oblique astigmatism, so it will form a circle of least confusion. And since the retina is not flat but it is curved, then this circle of least confusion will form on the retina, so it will be falling on the same curvature of the retina, eliminating its blurring effect. Also, the image formed by the oblique astigmatism fall on the retinal periphery, which has a poor resolving power than the macula or than the center. So we know that the density of photoreceptors is much more in the center than in the periphery, so that we appreciate the image falling on the center much more than the periphery. So if the image of the periphery has a coma shape or has irregular astigmatism or oblique astigmatism, it will not be much better or much more appreciated. Finally, we have the curvature of field. The curvature of field aberrations. It means that if we have a plane object, this plane object will give rise to a curved image. So you may wonder why this occur. Why do, if we have a plane object or a straight object, this object will cause a curved image? Again, this is because of spherical aberrations and the coma aberrations and oblique astigmatism. Even if they are eliminated, this can also occur. And this is simply due to unequal refraction itself, different refraction by the center and the outer part of the object. So this is dependent or this effect, this is for MCQ, that the effect of the curvature of field is dependent on the refractive index, number one, and the curvature of the lens surface. This is the second factor. And this is so it will be dependent on the refractive index and the curvature of the lens, and it is caused by the light rays from the outer limit of the object plane come to a focus near to the lens than the axial rays. So if we can notice here that the periphery or the outer part of the object will make a focus. This focus, it is much more closer to the lens, while the light rays from the center of the target or center of the object will pass through the center of the lens and will make an image that is more far from the lens. So since the outer part or the extremity of the object will make a focus more close to the lens, this will result in the curved appearance of the image. As we can see here, this is the light rays entering from the center. It will go through the lens and then it will refract, causing no problem. However, the light rays from the periphery of the lens, like here and there, will cause that the periphery of the lens or the periphery of the image is more curved. So this will leading to what's called curvature of field aberration. So how can it be neutralized? This can be neutralized by the written curvature. So if we have a straight object like this, and it will pass through a lens, and this object will leading to formation of a curved image like this. So this can be neutralized simply by the curvature of the retina. So the retina is curved and not a flat surface. So since it is curved, then this curvature of field aberration will be perceived by a curved retina, so it will be perceived as a straight.